The night sky, due to its potential to go supernova soon, if it were placed where the Sun is, would extend out to the orbit of Jupiter, demonstrating its massive size and unstable nature. This red supergiant is teetering on the edge of an explosive transformation, which could occur in the not-too-distant future. When it eventually explodes, the resulting supernova would generate more energy than a billion suns and become one of the biggest radio energy explosions in the entire universe. Such an event would have profound scientific implications, allowing astronomers to study a massive star's final moments and the supernova dynamics in unprecedented detail. Scientists and the general public alike are eagerly anticipating this rare cosmic spectacle. Betelgeuse has a diameter approximately 700 times greater than that of our Sun. If placed at the center of our solar system, it would engulf all the inner planets, including Earth. This colossal size places it in a special category of stars called red supergiants, which are known for their relatively cool surface temperatures and extended atmospheres. Despite their cool exteriors, red supergiants like Betelgeuse are some of the universe's most powerful objects. The star's energy output and rapid changes in brightness are signs of an impending explosion. Stars of this magnitude don't last forever, and when their nuclear fuel runs out, they end in a spectacular supernova. The reason Betelgeuse is so closely watched is that it has already entered the final stages of its life cycle, having exhausted the hydrogen in its core and now fusing heavier elements like helium, carbon, and oxygen. This progression is a ticking clock, indicating that Betelgeuse could explode at any time, whether tomorrow or within 100,000 years. In astronomical terms, the excitement around Betelgeuse's potential supernova reached new heights in late 2019 and early 2020, when the star dimmed dramatically, losing about 2/3 of its brightness over a few months. Although the dimming was later attributed to a large dust cloud ejected by the star, it served as a reminder of the instability in dying stars. When Betelgeuse finally goes supernova, it will be visible from Earth with the naked eye, shining as brightly as the full moon for weeks or even months. This spectacle would captivate not only scientists but also the general public, as Betelgeuse's position in the familiar Orion constellation makes it a recognizable feature in the night sky. Beyond its visual display, Betelgeuse's supernova would have significant scientific implications. Supernovae are responsible for distributing heavy elements like carbon, oxygen, and iron, essential for the formation of planets, life, and future generations of stars. Betelgeuse's explosion would provide astronomers a chance to study the dynamics of a nearby supernova in real time, helping us understand the behavior of stellar remnants and the physics of stellar explosions. One of the primary scientific goals would be to observe the formation of a neutron star or potentially a black hole. If Betelgeuse's core collapses into a neutron star, it will become a compact object made entirely of neutrons. If the core is more massive, it could collapse further into a black hole, an object with gravity so strong that not even light can escape. Moreover, Betelgeuse's supernova would release an enormous amount of neutrinos, subatomic particles that are difficult to detect but crucial for understanding the physics of stellar explosions. Neutrino detectors around the world would be on high alert to capture these elusive particles, providing clues about the processes inside a star during its final moments. Although Betelgeuse is about 640 light-years away, relatively close in cosmic terms, the supernova would not harm life on Earth. Our atmosphere would absorb the radiation from the explosion, including ultraviolet light and gamma rays. Nevertheless, scientists could still study the effects on our solar system, potentially learning about impacts on the Earth's atmosphere and space weather. Betelgeuse's supernova would also have a profound cultural impact. Humanity has always been fascinated by the stars, and such a major astronomical event could inspire a resurgence of interest in space exploration. People around the world would likely respond with artistic, literary, and philosophical interpretations, seeing it as a reminder of the vastness and beauty of the universe. The event could also drive advancements in observational technologies, refining instruments to better capture similar events in the future. As astronomers continue to monitor Betelgeuse for any signs of its imminent explosion, they are using techniques like spectroscopy, which analyzes the light emitted by the star to determine its chemical composition and temperature. Spectroscopic observations during the 2019 to 2020 dimming revealed that the star had ejected a large dust cloud, partially obscuring its light. Another technique, interferometry, involves combining light from multiple telescopes to create detailed images of the star's surface. These observations show that Betelgeuse's surface is dynamic, with large convective cells rising and falling as hot gas bubbles up from its interior. Despite these observations, direct monitoring of Betelgeuse's core is impossible due to its distance from Earth. So much of what we know is based on theoretical models. These models predict that when Betelgeuse finally goes supernova, it will experience a rapid increase in brightness as its outer layers are blown off in the explosion. This brightening will be followed by a gradual decline as the remnant expands and cools. However, uncertainties remain, and some models suggest that Betelgeuse could have a series of smaller eruptions before the final explosion. The impending supernova of Betelgeuse will not only provide a chance to witness a once-in-a-lifetime cosmic event, but will also serve as a reminder of the interconnectedness of the universe. The elements forged inside Betelgeuse over millions of years are the same as those making up our planet and bodies. Its explosion will contribute to the ongoing cosmic recycling process, seeding space with the building blocks for future stars and planets. While the timing of Betelgeuse's supernova is uncertain, this uncertainty only adds to the excitement and anticipation surrounding the event. Astronomers will continue to monitor Betelgeuse using a variety of techniques to observe its final moments and gain deeper insights into stellar evolution and the ultimate fate of massive stars. When Betelgeuse explodes, it releases a vast amount of energy and material into space. This material, enriched with heavy elements like carbon, oxygen, and iron, mixes with the interstellar medium, the vast clouds of gas and dust that fill the space between stars. Over time, this enriched material can collapse to form new stars and planets, continuing the cycle of stellar evolution. In this way, supernovae act as the engines of cosmic recycling, ensuring that the universe remains a dynamic and evolving system. The explosion of Betelgeuse would also have implications for the study of cosmic rays, high-energy particles that travel through space at nearly the speed of light. Supernovae are one of the primary sources of cosmic rays, and Betelgeuse's supernova would provide an opportunity to study how these particles are accelerated to such high energies. By observing the interaction of the supernova shock wave with the surrounding interstellar medium, scientists could gain new insights into the processes that generate cosmic rays. These observations would be particularly valuable for understanding the origins of the most energetic cosmic rays, which remain one of the great mysteries of astrophysics. Betelgeuse's supernova would also offer a unique opportunity to study the behavior of magnetic fields in and around the dying star. Magnetic fields play a critical role in shaping the structure and dynamics of supernovae, but they are notoriously difficult to observe. However, by studying the polarization of light from Betelgeuse's supernova, astronomers could map the star's magnetic field in detail, providing valuable information about how magnetic fields influence the explosion. These observations could have broader implications for understanding the role of magnetic fields in other astrophysical phenomena, such as the formation of black holes and neutron stars. The potential for Betelgeuse to produce a black hole is one of the most tantalizing possibilities surrounding its supernova. While it is uncertain whether Betelgeuse's core is massive enough to collapse into a black hole, if it does, the event would provide an unprecedented opportunity to study the formation of these enigmatic objects. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They are among the most extreme and mysterious objects in the universe, and studying their formation is one of the great challenges of modern astrophysics. If Betelgeuse were to form a black hole, it would likely be detected through the emission of gravitational waves, ripples in spacetime generated by the acceleration of massive objects. Gravitational wave detectors like LIGO and Virgo have already revolutionized our understanding of black holes by detecting the mergers of black hole pairs. But detecting the formation of a black hole from a supernova would be an entirely new frontier. Such an observation would provide direct evidence of the collapse of a massive star into a black hole, offering new insights into the extreme conditions that govern these events. Even if Betelgeuse does not form a black hole, it could still leave behind a neutron star, one of the densest objects in the universe. Neutron stars are the remnants of massive stars that have undergone supernova explosions and are composed almost entirely of neutrons packed into a sphere just a few kilometers in diameter. The intense gravity of a neutron star causes its matter to become compressed to extreme densities, and studying these objects can provide valuable insights into the behavior of matter under such extreme conditions. If Betelgeuse produces a neutron star, it could be detected through the emission of X-rays and radio waves, which are often associated with these compact remnants. Beyond the immediate scientific and observational benefits, Betelgeuse's supernova would likely inspire a new generation of astronomers and space enthusiasts. The sheer spectacle of the event, combined with the excitement of witnessing a supernova in real time, would undoubtedly capture the public's imagination in much the same way that the 2017 solar eclipse sparked a wave of interest in astronomy. Betelgeuse's supernova could lead to a renewed focus on space science and exploration. The event could inspire young people to pursue careers in astrophysics, engineering, and related fields, helping to advance our understanding of the universe for generations to come. The explosion of Betelgeuse would also prompt a reevaluation of our understanding of stellar life cycles. While astronomers have a general understanding of how stars evolve and die, each supernova provides new data that can refine and improve these models. Betelgeuse's supernova, occurring so close to Earth, would offer an unprecedented opportunity to test and validate theories about red supergiant core collapse and the mechanics of supernova explosions. The data collected from this event could lead to new discoveries about the physics of massive stars, potentially rewriting textbooks and reshaping our understanding of stellar evolution. One of the central questions surrounding Betelgeuse's supernova concerns the mechanics of the explosion itself. While we know that core collapse triggers the explosion, the details of how the star's outer layers are ejected remain an area of active research. As the core collapses, it produces a shock wave that propagates outward, pushing through the star's outer layers. This shock wave must overcome the immense gravitational force of the star in order to eject its material into space. However, not all core collapse supernovae result in a successful explosion. In some cases, the shock wave may stall, causing the star to collapse into a black hole without a bright supernova display. Observing Betelgeuse will provide valuable data on whether the shock wave stalls or successfully ejects the outer layers of the star. The role of neutrinos in triggering the explosion is also an area of intense interest. During the core collapse, the infalling material generates an enormous number of neutrinos, tiny, nearly massless particles that rarely interact with normal matter. These neutrinos carry away a significant amount of energy, and some models suggest that they may help to revive the stalled shock wave, allowing it to continue outward and explode the star. If Betelgeuse's supernova occurs during our lifetime, neutrino detectors around the world would be poised to capture the flood of neutrinos emitted during the explosion. Such a detection would be crucial in testing our understanding of how neutrinos influence supernova dynamics. In addition to shedding light on the physical processes driving supernova explosions, Betelgeuse's supernova would offer a unique opportunity to study how such an explosion interacts with its surrounding environment. Betelgeuse has been shedding mass for thousands of years, forming a complex web of gas and dust around the star. When the supernova shock wave collides with this material, it will create a brilliant, rapidly evolving display of light across many wavelengths, from radio waves to X-rays. By studying how the shock wave interacts with this circumstellar material, astronomers can learn more about the final stages of mass loss in red supergiants, as well as the broader impact of supernova explosions on their surrounding environments. This interaction between the supernova and its surroundings could also have implications for the formation of cosmic dust. Observations of supernova remnants have shown that supernovae are prolific producers of dust, but exactly how this dust forms and survives in the harsh conditions of space is not fully understood. Betelgeuse's supernova would allow astronomers to observe the dust formation process in real time, potentially providing new insights into how dust grains form in the aftermath of a stellar explosion. This is significant because cosmic dust plays a critical role in many astrophysical processes, including the cooling of gas clouds, the formation of stars, and the growth of planetary systems.